Michael.
On the back side, CC.
On which one?
CC, the defensive tackle.
Well, we can't look at just C. You got to look at the whole thing. Okay. So here's the deal. So you got a fullback. Okay. Slides in midair. Defensive tackle. Opposite directions. Both end up with 0 velocity. So you got one guy going in one direction. You got the other guy going in the other direction. They're going to hit and they're just going to stop. Now the beauty of this is you're treating this as like idealized situations, okay? So you're not going to have any situation where like they're still pushing off each other. In other words, this is just a pure momentum analysis, okay? This isn't, oh, Bubba is still pushing, the other one is still pushing, that gets weird. So here's the situation. So when you get done, they're going to come in and they're going to collide. So afterwards, what's their total momentum? 0. So again, every momentum problem starts the exact same way. So you got the momentum of the fullback plus the momentum of the tackle equals the new momentum of the fullback plus the new momentum of the tackle. Start this way every time, okay? Do not shortcut this process. So when you get to that point, okay, when you get to that point, what does this side over here have to equal?
The same.
Well, it's going to, this whole thing is 0, right? Okay, because they're going to hit and they're going to stop. So what does that mean in terms of, so these two momentums over here have to be what?
Equal and opposite.
Equal and opposite. So the momentum of one had to equal the momentum of the other one. So the only way that can happen is if one is positive and the other one is negative. So their momentum vectors are pointing like this. Okay? So when you look at 2A, what's the fullback's momentum for the collision? That should be like around 760. So if that's 760, what's the new what momentum did the tackle have to have?
Negative.
Negative 760. Okay? And then once you get that, then change in momentum is momentum final minus momentum initial. So this 760 and the negative 760s are these numbers. Well, what's the final momentum of both of them? 0. So it's going to be 0 minus 760 and 0 minus a negative 760. So on number 2, you should have a lot of the same answers. That's just going to have different signs. Okay? Now, on number 3, make sure that you realize that in big bold letters I told you that Bubba and Leroy are moving in the opposite direction. So, number 3 is going to start the same way number 2 did. So on number 3, start off this problem going, okay, I got the momentum of Tony, plus the momentum of Bubba, plus the momentum of Leroy is going to equal the new momentum of Tony, plus the new momentum of Bubba, plus the new momentum of Leroy. They all start the same way. Don't shortcut this process. So then, what happens over here? What can you do over here? They all stick together, right? So what can you do when they all stick together?
Vector out of velocity.
Yeah, so this is going to be the sum of the masses. There's a horrible sum. The sum of the masses times V prime. So you've got everything that you've got to know over here. But here's what you have to realize. They're moving in opposite directions. So what are you going to have to do with one or two of the velocities? Yeah, one of them has to be negative value. Okay, 1 or 2, I don't care how you define it. So what you're searching for is that V prime. So if all goes well, that answer on number 3, that new velocity, should be a really, really small velocity, like 0.0 something. Okay? Now, on number 4, let's talk, especially when you get to 4F, okay? So I'm going to throw out 2 different situations and you tell me which one's right. So on 4F, you can look at this in terms of a velocity time graph. So there's two different situations you can show on this velocity time graph for 4F. One is the velocity time graph goes like this, and it goes from 218 down to 80. The other option is that it's going to go from 218 down to negative 80. So which one is it?
Negative 80.
Negative 80. Why?
Because it's going the opposite direction.
Yeah, so you have to stop this thing, have it change direction, go through 0, and then speed it back up. Because if you do this, if you just go from 218 to positive 80, then it never shows the direction change because the velocity never changes sign. So be very careful about that one on 4F, because that's the most common mistake that's made on 4F. Now let's talk about number 8. Okay, where you've got to draw the velocity time graph, where you've got a slight uphill. So in number 8, visualize this. You got a little bit of an uphill slant, okay, not a whole lot. And here are the two carts, okay, and you got more mass on this one. It's going to push off. So here's the deal. Where on both graphs, where are you going to start on number 8? 0, because everything was at rest. So your velocity time graph is going to start something like this, where you're at 0. Okay? That's where that thing's going to start. So obviously, one of these is going to go in one direction, the other one's going to go in the other. So you're going to hit the plunger, and I tell you, this one with the more massive one is defined as positive, and that's going uphill. Okay? So you're going to have this one going up, you're going to have one of them coming down. So it's basically going to start pretty similar to what happened with the pre-lap graphs that you drew. Okay? So that's going to be pretty similar. But as this one goes up, here's what's going to be important. As this one goes up, is it going to speed up or slow down after that plunger expands? Slow down. It's going to start to slow down. What's this one going to start to do after the plunger expands? It's going to keep speeding up, okay? But probably not at the same rate that it was when that plunger exploded, okay? So when you get done with this graph, it's going to start off something like this. If you want these two lines to be parallel, you draw them so I can clearly see that they're parallel. If you think they're not parallel, then you draw one pretty shallow and the other one steeper so that I know which one you think has a more shallow line and which one has a steeper line. I'm not going to guess if they're parallel or not. If you want them to be parallel, you physically draw them being parallel. If you think they're not parallel, then you draw them so that I know, oh, hey, you think these lines aren't parallel. Okay? Because they're two distinctly different things. So if you want them to be parallel, make sure I see that they're parallel. If they're not parallel, make sure that I see that as well. Okay? Anything else? Make sure somebody hands in that pre-lab graph. Okay? I don't care who, just make sure somebody stays with it with their stuff. Okay? We're good? Going once, going twice, sold. All right, Mad Max. Okay, so here's kind of a good news day. We're going to work through this big complex problem. Then we're going to watch a video on crashes, and you don't have any homework tonight. So,
Good news, good news.
yeah, it's kind of good news all the way around.
That's
Okay,
very good news.
so here's the story. Your test, which I need to change that, is next Tuesday. It is not Thursday, it's next Tuesday. Because we basically are done with linear momentum. We've got to do angular momentum, which we'll do tomorrow and Friday. Review on Monday, test will be on Tuesday. So that's kind of the setup. Now, I promise you, there's going to be a problem like this on the test. I'm going to change the numbers, okay? But it incorporates a whole bunch of different things. So again, I beg of you, I'm going to tell you exactly how to work this problem. I'm going to show you all the subtleties. I'm going to tell you exactly what I'm looking for. Between now and then, that test, work this problem a couple of times, change up the numbers, change the heights, change the mass, whatever, okay? Because we're going to work through this whole thing, and you know this problem is going to be on the test. So don't act like I'm going to give you the test and go, God, where Kemp didn't tell us about this problem. Almost gone. Okay, so here's the setup. There's a couple, and I'm going to play this exactly the same way on the test. I'm going to define everything the exact same way. The ground is going to be the reference point, so that's 0 meters. Anything going down is going to be defined as being negative. Anything going up is going to be defined as positive. I'm going to have the exact same system on the test, okay? There won't be any variation on this thing. So here's the basic setup. I'm going to drop this golf ball, it's going to hit the ground, and it's going to drop from a height of 1.8 meters and 1.85 meters. It's going to hit the ground, and it's going to bounce back up to a height of 1 meter, okay? That's what you know. It's in contact with the ground for 1.28 times 10 to the minus seconds, which isn't very long, okay? So you're just basically, boom, it's a very short amount of time for this to happen. So that's all the information that you've got. So there's a whole bunch of things that you want to find. We're going to find like the velocity time graph, we're going to find the change in momentum of the ball, the change in momentum of the earth, the force exerted on the ball, the acceleration of the ball, whole bunch of different things, okay? Now, here's the other thing that, and before we even start on the numbers, we're going to look at this from like a holistic standpoint, big picture kind of thing. So, let's just look at this in terms of what the velocity time graph is going to look like. Now, I know we don't have any numbers yet, okay? We will. But we're just going to look at this in terms of what's the velocity time graph going to do. So, first off, where's the velocity time graph going to start? 0. Why? Yeah, I'm just dropping the ball, okay? I'm not going to make this complicated and throw it up in the air or throw it down, okay, or throw it horizontally, okay? Boom, we're going to drop the ball, okay? No worries. So, we're going to drop the ball, so my velocity time graph is going to start here. It's going to do one of two things. It's either going to slope up or it's going to slope down. Hunter, your thoughts? Slope up, slope down?
Gonna slope
Slope up. Why?
because it's positive and then at some point it has to cross 0 because it changes direction.
This is true. But keep in mind that anything going down is going to be negative value. So I'm going to start here, right? So what's going to be the sign of the velocity once I let go of it?
Negative.
So what does this graph need to do?
Slope down.
Yeah, because if you started here and you started up, then you're saying, I'm going to drop this ball, which would be cool. And then it's going to start accelerating upward. Okay? Cool, don't get me wrong, right? Not going to happen. So, it's going to start here, and it's going to slope down. Now, great. What's the slope of that line?
Negative 9.8 meters per second squared.
Why?
Acceleration of gravity, and that's the only force acting on it.
Yeah, as soon as I let go of it, what's the only force in town? Gravity. And you know what acceleration that's going to cause. Oh, okay. So that's going to be negative 9.8 meters per second squared. Okay? That's going to be the slope of this line. It's going to be coming down like this. Now, at this point, it's going to hit Mother Earth. Okay? Now, I don't know what this velocity is. I'll find it later. Okay? I'm not worried about it for now. This is a big picture kind of problem. So, going to hit this ground. Now, at that point, okay, at that point, it comes in contact with the ground. So what's this graph going to do? It's going to do one of three things. It's either going to slope up, it's going to slope further down, or it's going to be a horizontal line. Mad Max.
It's going to slope up
Why?
because it's changing direction. It's slowing down in the negative direction, and then it hits 0 and changes direction and starts moving positive.
Okay? You think that's going to be a pretty steep line or a pretty shallow line?
Pretty steep
Why?
because it's going to have a change from a negative to a positive velocity in 1.28 times 10 to the negative seconds.
Yeah, this whole thing is going to happen pretty quickly. Okay? It isn't like we're going to catch the ball, stop it, give it a thought. Okay, I'll throw it back up. Okay? No, this thing goes doink. Okay? It's a very, very short amount of time. So the line's going to come up here, like this, okay? So here's the question. Mary, what's the sign of the acceleration through here? Positive or negative?
Positive.
So what does that mean? What's the ball doing?
It's gonna start going back up.
Not until we cross it.
Oh, it's slowing down.
It's just slowing down, right? Because I've got a positive acceleration and
Negative velocity.
or slow down, right? So physically what's happening is that this golf ball, or all golf balls, are made up of polymers that basically instantaneously they compress and they store energy, okay? They store energy by forming a small compression. So if y'all remember, when we did the lab where you pushed the cart, and there was a spring on the front of it, and it hit the wall and it sprung back, okay? And then you could see like the spring being compressed. That's what's basically happening with that golf ball, okay? That golf ball is being compressed, so it has material that can get distorted and store potential energy, and then release that energy and make that ball go back up.
So that
Right?
that whole time that it's going up to zero is just it's compression.
Yes. So all that's happening here is that on an atomic level, think of this as like a spring, and you're storing that energy in that compression. Now remember, Mother Nature and potential energy don't like each other, okay? So Mother Nature is going, oh, you think you're clever. You can store that potential energy. Well, screw you. Because what's Mother Nature going to make that ball do with that potential energy?
Release it.
Change it into
Kinetic energy.
kinetic energy, energy of motion, right? Because Mother Nature goes, you're not going to get a store of that. So, at this point, this is when that ball has undergone maximum compression. So on an atomic level, all those particles are storing all this energy. And he goes, seriously, dude, can't keep it. Got to go. So, at this point, the velocity is 0 meters per second. You're on the ground, you've undergone maximum compression. So at this point, little particles are going, oh, fly, be free. So one of three things is going to happen at this point. It's either going to keep going up like this, it's going to turn into a horizontal line, or it's going to start back down like that. Olivia, what's it going to do?
It's gonna slope up.
Slope up. Same slope?
It's a little less steep
Why?
because it took like no time for it to compress. So it's not gonna go up as fast.
Oh.
That's-
Hold that thought. Great?
Will its slope be positive 9.8 meters per second? Oh, okay. Nope. Never mind. I don't know. I was thinking maybe it's just gonna flip the sign and then it's gonna.
Yeah, we just changed gravity real quick.
Yeah.
Yeah.
Okay, stop. Stop.
Oh wait, no. Oh. Okay. Yeah. No, I don't get it. I don't get it.
You had it, and then you didn't have it.
Yeah, I don't get it.
Okay,
It slowed down.
so at this point, is the ball stopped? Why does it have to stop?
It's changing direction.
Change the direction. So at this point, it's going to start to speed up, right? Because now that stored energy is going to be pushing against gravity, and it's going to push that thing up, right? So here's the question. This is what you have to understand. So imagine that we're looking this under like a high-speed camera. The ball is going to hit here. You're going to compress and store energy. You're going to be fully stopped. This is when you have maximum compression. Then that ball is going to expand, and it's going to propel that ball back up. Now, what if I did this with an egg?
It'd just break and stop.
At this point, what would the line do?
Just be horizontal.
Yeah, it would just be a horizontal line, right? Because that egg is not going to bounce back, right? Watermelon, grape, whatever it is, okay?
The grape would balance actually.
Grape
It might bounce a little bit.
But
Maybe.
grape wouldn't bounce.
Okay,
Depends on how high you drop it.
yeah, that is true. You can drop it from like, yeah, probably not going to bounce.
Always bounce back.
Okay. You always bounce back. Well, look at your finger, man. You're
Yeah, I
like
know.
cast free. You can
Uh-huh.
turn.
That was a nasty
Oh, there
work.
we
And
go.
taking the
After the
pins out of your
season.
finger,
Yeah. Okay.
that was gross.
So here's the deal. So you're compressing the ball. You're fully stopped. You're expanding it. Now, at this point, you're going to leave the floor. Okay? Now, this is why you look at this in terms of a big picture. Okay? You want to look at this in terms of a big picture. At this point, the ball has just, literally, just left the floor. Why is this velocity now positive? It's going up, right? Now, here's the $1 million question. Let's just say, just to make up a number, okay? Let's just say this number is negative 8 meters per second, okay? I don't know what it is. I'm just going to say, let's just say, hypothetically, it's negative 8. It's not, but let's just say. So would this positive velocity here have to be bigger or smaller than negative 8?
Small.
Why smaller?
So still, you have a force acting on it, pushing down.
Why did gravity, I had a force acting on it pulling it down too?
Yeah, that's true.
Nick?
Well, because some of the force is going to be left when it hits the ground, so it's not going to have as much to actually push it back up.
So?
So
You're
it's gonna be
right.
smaller.
So maybe like 6?
Yeah.
Okay. So here's the $1 million question. Nick's right, okay? But let's play the what if game. What if this that hit at negative 8? Let's say it left at positive 8. What would it do?
It would bounce right back up to where it
It would
started.
go back up to 1.85 meters, okay? Which would be the ultimate physics demo to do. Okay, so if every physics lecture in the world wants to have happen, to be able to drop a ball at the beginning of a lecture, okay? And then give the entire lecture and the ball continues to bounce back up to the exact same height from which you dropped it. Okay? It would just be cool. It's like, what do you, of course, no one would pay attention because y'all be watching the ball go back and forth. Okay? Y'all be like, what? Did you say something? No, seriously. Okay? I just watched the ball. Y'all get mesmerized. So, here's what we know about this velocity. Number one, it has to be positive because it's going up, right? But it has to be less than the velocity that it had when it hit. Okay? So there's two things I know. It's got to be a positive velocity and it has to be a smaller value than when it hit. So at this point, it leaves the surface of the floor. Okay? It's gone. Boom. It's on its way up. Leslie, as soon as it leaves the floor, what does it start to do? Slow down. At what rate? Say that louder.
Negative 9.8 meters per second.
So what's this line going to do then? As soon as it leaves the floor, what's it going to do?
Go down.
Is it going to be the same slope as this line?
Yes.
Yes. Because in both situations, guess what? The only force acting on it is gravity. So this line's going to have a slope of negative 9.8 meters per second squared. This line's going to have a slope of negative 9.8 meters per second squared. Now eventually, this line's going to cross 0. When it gets back to 0, where's that ball at? At its
Max height.
maximum height. Okay? So, this is what you're going to have to draw on the test. Okay? I promise you. I'm going to say, hey, sketch the velocity time graph. You're not going to have to know the specific times. Okay? I won't make you find those. But you are going to need to know the general shape of this thing. Okay? So, you start at 0, straight sloping line, going to hit, going to speed up, going to leave, and then it's going to slope. And here's what I'm going to look for on the test. That this line here is parallel with that line there. Because that way you're showing the exact same acceleration of negative 9.8 meters per second squared. Cool so far? Got it. Okay. Now, let's see if we can figure these out. So, let's just look at what's going to happen on the way down. we got 1.85 meters. When I drop it, what's my initial velocity?
0.
0. Don't make this difficult. I'm not going to throw it, toss it. V naught's going to equal 0. What else do you know?
Acceleration.
Acceleration's going to be
Negative 9.80.
negative 9.8 meters per second squared. But I'm trying to figure out velocity just as it hits. So I know an initial velocity, a distance, and an acceleration, and I need to find a final velocity. So what am I going to do?
Use that.
Use that equation. So I'm going to go, oh, okay, so this is on the way down. Okay? So I'm going to go v squared equals v naught squared plus 2ad. So here's the $1 million question. Am I looking for v naught, or am I going to look for v?
V.
V. Why? So I find a velocity on the way down. So I'm going to have v is going to equal
280.
v naught squared plus 2ad. V naught is going to equal 0. Now, what I'm about to do is wrong, okay? Do not do what I'm about to do. It's wrong. Yeah, okay, hey, this is easy. I can physics, okay? Negative 9.8 meters per second squared times 1.85 meters. So I've got my acceleration, negative 9.8 meters per second squared. It's following 1.85 meters, and I got 0 squared. So why is this going to be a train wreck?
You have a negative number under the radical.
I got a negative underneath the radical. Home. Won't work. So we can fix this a couple of ways. We can just ignore it and hope it goes away. Okay? And hopefully Burkamp won't see that when he grades my test. What are the odds that's going to happen? 0. Okay? We could just go, oh, I'll just make it positive. Problem solved. Could you do that? No. Why not?
Gravity doesn't travel up.
Yeah. Look at you. You have to stick with what brought you to the show. If your velocity time graph is going to have a negative slope of negative 9.8 meters per second squared, guess what? You have to stick with that throughout the entire thing. So I can't make that negative, okay? But can I make the 1.85 negative?
Yes.
Now, can I just randomly make it negative?
No.
There has to be a mathematical basis for it. So here's the trick. When this thing lands, what's its final position? Lands, its final position is 0. What's the initial position?
1.8.
1.85 meters. How do you calculate displacement?
Final
Final minus initial. If I take 0 minus 1.85, I get
Negative 1.8.
negative 1.85. Miracle of miracles. Now that's cool. I promise you on the test, I'm going to go through your work, and you better show me both negative signs underneath that radical. Okay? I promise you I'm going to look for that. Okay? So when you work this problem again, make sure that you are consistent with these signs. Now, somebody run the numbers. Take basically 19.6 times 1.85 and then the square root of that.
6.02.
6.02. So, is that my velocity?
It's negative. Because it can be positive or negative, but you have to choose negative.
Which direction is it going when it lands? How do we define down?
Negative.
But you're taking the square root.
So it's positive or negative.
Square root is positive or negative. What do you have to do?
Choose
You
the
just
one
have
that
to
makes
choose the
sense.
negative root. Okay? You just have to choose the negative root. So I got negative 6.02 meters per second. Good with that. So at this point on our graph, we know that this thing is going at negative 6.02 meters per second. Okay? That's the velocity that it's going to have when it lands. So now that I know this number, what do you know about the velocity that it has when it leaves?
Has to be less.
Has to be a positive number. And it has to be less than
6.02.
6.02. right? Because let's say you find this velocity and it's like 7.4.
Something horribly wrong.
Yeah, you can be higher than when you dropped it, okay? Even in Colorado in this experiment, you can't do that, okay? So it ain't gonna happen. So you know this velocity, when you find it, has to be a positive number less than 6.02, okay? That's what has to happen. If you get something like, let's say you get positive 8, no, it's wrong. It's not gonna work, okay? So this is why you want to think this problem through before you actually work it. You go, okay, hey, what am I going to get out of this deal? Oh, okay, right. Let's look and see if it seems reasonable. So here's the next thing. And you need to kind of work this thing in sections. So this is on the way down, right? Now I'm going to look at on the way up. So here's the question. On the way up, okay, so this thing is going to go up to a height of 1 meter. Here's the $1 million question. On the way up, am I searching for the final velocity or the initial velocity? The initial. Why? I know my final velocity is going to be 0. Okay? I know my final velocity is going to be 0. So here's what we're going to look at. Okay? Here's what we're going to look at. On the way up, we're going to use v squared equals v naught squared plus 2ad. True? That's what we're going to do. Cool with that. But what am I searching for? I'm searching for v naught. So how am I going to get v naught by itself?
Subtract 2.
Subtract
280.
2ad and then take the v naught. Now, this is a situation where you want to leave everything in here. Do not shortcut this. So on the way up, what's my final velocity? 0. Okay, I've got to have that in there. Okay, I've got to have that in there. Minus 2, what's my acceleration? Negative 9.8 meters per second squared. Now, on the way up, am I going to put that in as a positive 1 meter or a negative 1 meter? Why?
Starting from 0 to ground.
I'm starting at 0 and ending up at
1.
1 meter.
Or 1. Yeah.
Okay? So my displacement is going to be positive 1 meter. Now, is this going to work mathematically?
Yes.
Why?
Because you're subtracting the negative.
Yeah, I've
from
got a
0.
negative, I've got 0 minus a negative number. This is why you have to have this 0 in here. Okay? You just can't pretend that it's not there. That 0 has to be there. Okay? So you might even kind of go, ooh, remember that. Okay? Remember the 0. So, crunch the numbers. What do you get?
4.43 meters per second.
4.43 meters per second. Positive or negative? Why?
Going up.
This is going up. Okay? Good with that.
Yes.
Okay. Now, pretend that you don't know any numbers. Pretend that we have calculated no numbers. Okay? Pretend that you don't know anything about the actual numbers. So, I want to find the change in momentum. So what are the two things that change in momentum equals?
Force times time.
Mass and, or I'm going to write as V minus V naught. And it also equals,
Force times time.
so which route do you think I want to go? Mass delta V, force time.
Mass delta V.
Yeah, you don't know the force, okay? You don't know the force. But I do know the mass, and I know V minus V naught. Now, here's the trickiest part of this entire problem. Okay, here's the trickiest part of this problem. You're looking at this change in momentum when it hits the ground. Okay, so that's what we're focusing on. We're not talking about when it's falling. Okay, listen to me. I'm not talking about when it's falling. I'm talking about when it's in contact with the ground. Okay, huge difference. So here's the million-dollar question. Is this V, okay, is that going to be the velocity on the way up, or is that going to be the velocity on the way down?
Velocity on the way down. Oh wait, no, sorry, on the way up. No,
Down. Down.
Hold on.
V
Okay.
naught is on the way
Think
down.
this through, okay?
V naught is on the way down.
We're looking at what's going to happen at this interchange, right? When it's going to hit the ground and bounce back up. When it hits the ground, okay, is that V or V naught?
V naught.
That's V naught, okay? So what do you know about the sign of the velocity when it hits the ground?
Negative.
It's a negative number. So when it hits the ground, that's going to be my V naught, which is going to be some negative number. Good with that. Now, when it leaves the ground,
Could I borrow Olivia Elmore real fast?
no.
All right.
Come back in about 10 minutes and you can.
All right, thank you.
So,
I don't want to miss this.
okay. So, I got you back. Okay.
That's a good teacher.
So, here's the deal. When it leaves the ground, is this going to be a positive or negative number? It's going to be a positive number. Okay? So, this is where this gets tricky, and this is what's going to require thought. Yes, I said the T word, thought. So, I don't care about the numbers for now. Is this a V, when it takes off, going to be a positive or negative number? Positive. So we're going to have a positive number minus a negative number, right? So when I take a positive number minus a negative number, what do I get? Another positive number. So I'm going to have a mass times a positive number for my delta V. So that means my change in momentum of the ball is going to be a positive number. Okay? Cool with that. This is the thought that you have to go through. And this is the hardest part, is this transition right here. Now, this is the other thing where this gets confusing. Okay? Unless you think your way through it, which I have the utmost confidence that all of you can do. So, when we found the velocity when it landed, we found V, right? Okay, we found the final velocity when it landed. But here's where this is tricky. You find V here, right? But in your change in momentum equation, that actually becomes V naught, because that's the velocity that it has when you're looking at that transition. So even though you're finding V out of that equation, it becomes V naught in the change in momentum when the ball was in contact with the floor. Hunter?
So is it the same numbers that we found, just switch them around?
No,
Or do we have to find
yeah, it is.
whole new numbers?
It's the exact same numbers.
Okay.
Okay? There's no, all we're going to look at is in what sequence we subtract them. Okay? Now, but again, when you look at what you're calling the final velocity here, okay, when it takes off, was the initial velocity that we found out of that second calculation. So when you find V on the way down, it becomes V naught in that transition. When you find V naught on the way up, that becomes V here. Okay? That's the most complex thing that you have to worry about. So you might put like a big box around this if you're writing it down going, ooh, think about this, okay? Right? So, in this situation, my mass is 254 grams, which is 0.254 kilograms. So 0.254 kilograms. So, in that exchange, okay, in that exchange, when it's hitting the table or the floor, whatever it is, okay? In that exchange is that 6.02, okay? The velocity that it had when it landed, negative 6.02. And the other velocity was what, 4.43.
Oh, you added.
So here's the question. Is the 4.43 V or V naught?
V.
That's going to be V. Ah, okay. So we're going to have 4.43 meters per second. Because that's going to be the velocity if that's what the velocity is going to have when it leaves. But it's going to hit at negative 6.02. So I'm going to have 4.43 minus a negative 6.02. And again, if there is something that you tend to screw up, it's going to be this. So make sure that you highlight that whole thing, that you remember that that's going to be minus a negative. Okay? All right. So what do you get out of this entire calculation then?
2.65.
2 point what?
65 newtons.
Positive or negative?
Positive.
Okay, so what that means, that's the change in the momentum of the ball when it hits the ground, 2.65. So remember this number. So we're going to start another screen here. So the change in momentum of the ball is going to be, was it 2.65?
Yeah.
So, what's the change in momentum of this rock that we're on? Don't make this difficult.
Negative 2.65
Negative 2.65. Why?
because that's equals 0.
Momentum has to be conserved, right? Okay? So, we're going to transfer some energy to make that ball bounce. Where does that momentum come from? Mother Earth. So the change in momentum of the Earth is going to be negative 2.65 newton seconds. So every time you bounce a golf ball, you're changing the momentum of the Earth. Okay? Going, whoo, nice. But if you jump up in the air, you've changed the momentum of the Earth. Not very much, especially if you have the ups that I do. Okay? But you can change it. Now, here's the question. Can I find the force exerted on the ball? How so?
Of course. You know the mass and you know the acceleration.
No, I don't know the acceleration.
Divide by 2.
Well, you know, force times time equals change in momentum. Do I know the change in the momentum?
Yes.
So, I know that force times time equals change in momentum. Now, let's just think about this for just a second. Is the sign of the force exerted on the ball going to be a positive or a negative number?
Positive.
Negative. Well, I don't know. It's a hard day.
Hey, he's trying.
I know. Well, look at it this way. If you're going to stop this ball and project it upwards, what direction is the force going to act? Upward, right? I'm not going to stop this ball and project it upwards by pushing it down. True? Okay? True enough. So the force exerted on the ball has to be a positive number. Oh, cool, right? So this is also why this fits. I notice for the ball I have a positive change in momentum. Okay? With a positive change in momentum, I have to have a positive force. Oh, that's kind of cool. So if I divide this by time, so somebody take 2.65 Newton seconds to divide that, what was that time? 1.28 times 10 to the minus
2.
second? Seconds.
207 newtons.
What'd you get?
207.
207 newtons. So does it make sense that that's a positive number?
Yes.
Because that's the direction that the ball is, bouncing up, right? Now, can I find the force exerted by the ball on the Earth?
Yeah.
Now, should that be a positive or negative number?
Negative.
That should be negative because the ball is going down, and Newton's third law says, oh, if you're going to have an upward force, guess what? You have to have a
Downward.
downward force, and that's the direction that the ball was going. Oh, cool. So, let's look at that magic. So, the change in momentum of the Earth, we said, was negative 2.65 Newton seconds. So, if I divide that by that same time, oddly enough, I get a force of negative 207 newtons. Oh, Newton's third law. That's kind of cool, right? So here's what we've got so far. And there's no exceptions to this rule. There's no tricks to it. Anytime you have an interaction, what do you know about the changes in momentum? They are equal and opposite. What do you notice about the forces?
They're equal and opposite.
They're equal and opposite. Okay? There is no exceptions to this rule. There are no caveats. It isn't just on Tuesdays at 12:30. Okay? Or when it makes sense, or when you have a ball hitting the earth, but that wouldn't work if it was like a kangaroo jumping up, or something like that, or if it only works in the northern hemisphere. No. Okay? There's no caveats to this law. None. Zero. Zip. There's no caveats. Okay. Could I find the acceleration of the ball?
Yeah.
Why?
Because you have force and mass.
I know the force and I know the
Mass.
Now, so let's find the acceleration of the ball. Oh, that's cool, right? So I know F equals ma. So I had a force of 207 newtons. So divide that by the mass of 0.254 kilograms.
815.
815 meters per second squared. Now, here's the million-dollar question, amongst many others. How does that 815 meters per second squared fit with that velocity time graph?
It'd be the slope going up.
And notice that that's a positive slope. So this line from here to here is going to have a slope of 815 meters per second squared. That's why this is so steep, and that's why that's sloping up like that. Great.
So between 0 and that peak, that's still, is that like still compressing?
No, no, well, it's compressing from here,
Uh-huh.
and then it's expanding from here.
But it's still like, it's not even, like, how does that looking like to us? Like, is it at
The ball's still on the ground.
it's still on the ground as
Yes.
it's going up?
Yeah, so imagine it's like the cart, where you had like, here was that cart lab that you did years, like about a month, 2 months ago. And you had the plunger,
Yeah.
and it would hit, so that when that plunger was compressing, that's like this portion of the graph.
Oh, it's just that again. But,
And then when that plunger was expanding, that's that portion of the graph.
okay.
Okay? All right, so we have one thing left to do, and then we're done. Can I find the acceleration of the Earth? You know the force exerted on the Earth,
Yes.
which is going to be
Negative 207.
negative 207 newtons. Mass of the Earth, 5.979 times 10 to the 24th kilograms. So somebody take 207 and divide it by 5.979 times 10 to the 24th. Is it going to be negative 815? No. Well, thank God, no.
It'd be pretty funny though.
What'd you get?
That's into the sun.
3.46,
Negative 3.46 times 10 to the
negative 23rd.
negative 23rd meters per second squared. Now, why don't we want the accelerations to be equal and opposite?
Because Earth,
Because Earth would
Yeah,
just
because
fly off.
imagine that the Earth accelerated out from underneath us right now every time that I drop that ball at negative 815 meters per second squared. Okay? You know, imagine basketball on, basketball season on a Friday night. You know, every small town in America has some kid playing basketball and bouncing that basketball, right? And if that was the acceleration of the earth every time that a ball bounced, you know, it'd be horrible. The earth would go, ah, okay, right? Or I'm after school, right? And, you know, you guys are out, you know, playing, practicing basketball. Somebody would dribble with the ball. I'm trying to grade papers. Well, the earth accelerates out from underneath us. Stop already, okay? So it's cool that it has a really small acceleration. So here's what I want you to understand. I'm going to ask you about 3 things when you have an interaction on the test. I promise you, these are going to be the 3 things I'm going to ask you about. I'm going to ask you about what happens to the force. I'm going to ask you about what happens with the change in momentum. I'm going to ask you about what happens to the acceleration. 2 of the 3 are equal and opposite. What are the 2 that are equal and opposite?
Force
And
momentum.
change in momentum. Okay? I promise you, I'm going to ask you those questions. It's going to be multiple choice in the middle of the front page. Okay? That's what they're going to be. What's the only way the accelerations are equal and opposite?
Same
Is
mass.
if they have the exact same mass. Okay? If they're not, the accelerations aren't equal and opposite. That's it. There you go. So I promise you, there's going to be a problem like this on the test. Mark my words. Between now and Tuesday, work the problem again and again and again. Guess what? I'm going to give you a problem like this on the review. Okay? Now, make sure that you pay attention when you're working these problems. Pay attention to the subtle things. Okay? The fact that, you know, when you're calculating your velocities, that you have negative 9.8 meters per second squared all the time. Pay attention to the sign of your displacements, whether those are positive or negative. Are your velocities positive or negative? So I beg of you, work this problem. You know what's going to be on the test. Okay? All right. So, we're done? So the video is on car crashes, and oddly enough, it deals with this whole idea. So, let's stop that.